Hello students, here I have come with the next lecture in the series of lectures about primary decomposition of ideals. Recall that in the last lecture we have discussed about first uniqueness theorem of decomposable ideals. So in this lecture I will first discuss about the one-to-one correspondence between primary ideals of ring A and the primary ideals of rings of fractions. And then we will discuss about the second uniqueness theorem for decomposable ideals. So let us start our lecture with this theorem, which says that if S is a multiplicatively closed subset of ring A and Q is P primary ideal, then if S intersection P is non-empty, then S inverse Q is the whole ring. And if S intersection P is empty, then S inverse Q is S inverse P primary. Moreover, in this case, QEC is equal to Q, where E is extension with respect to natural homomorphism from A to S inverse A, and C is the contraction with respect to F. So let us prove first part. Suppose that S intersection P is non-empty. So we take an element S in the intersection. Now S belongs to S and S belongs to P. Now Q is given to be P primary, so P is radical Q. So this means Q contains some positive power of S. Let Sn belongs to Q. Also, S is a multiplicatively closed set, so Sn belongs to S. So Sn belongs to Q. This means Sn upon 1 belongs to S inverse Q. Now Sn is in S, 1 is in S, so this is unit in S inverse A. So now S inverse Q is ideal of S inverse A, which contains a unit. So this is the whole ring. So thus, if S meets P, then S inverse Q is the whole ring. Now, let us assume that S does not meet P. Now, remember, there is one-to-one correspondence between prime ideals of ring A and prime ideals of ring A which do not meet S and prime ideals of S inverse A. Now, P is a prime ideal of ring A which does not meet S. So this means S inverse P will be prime ideal of S inverse A. So thus, S inverse P will be proper ideal of S inverse A. Now, we want to prove that S inverse Q is primary and radical of S inverse Q is S inverse P. So to prove that this is primary ideal, first of all we need to prove that this is proper ideal of S inverse A. And then we will prove the other property. Now since radical of S inverse Q is S inverse radical Q, which is equal to S inverse P, which contains S inverse Q. Since this is a proper ideal, so this is also a proper ideal. So now let us take product of two elements in S inverse Q. X by S and Y by T. This means XY by ST belongs to S inverse Q. This means XY belongs to Q. Since Q is given to be primary ideal, so either X belongs to Q or Y belongs to radical Q, which is equal to P. That is, either X belongs to Q or Yn belongs to Q for some n greater than equal to 1. This means either X by S belongs to S inverse Q or Yn by Tn belong to S inverse Q. Because T is in S, so Tn will belong to S. That is, Y by T belongs to radical of S inverse Q, and hence S inverse Q is primary ideal of S inverse A. So thus, if S does not meet P, which is radical of Q, then S inverse Q is primary ideal of S inverse A. Now we want to show that if S intersection P is empty, then QEC is equal to Q. Now recall that we have done QEC is union of such kind of ideals Q colon S, where S belongs to S. Now since S does not meet P, here it should be empty. So here we can write union S does not belong to P, Q is to S. Now in the previous lecture we have shown that if S is not in radical Q, then Q is to S is nothing but Q. So therefore, we get QEC is union of Q, which is Q. So thus, if S does not meet P, then QEC is Q. Now we are able to prove the correspondence theorem between primary ideals of A and primary ideals of S inverse A. It says that there is one-to-one correspondence between the primary ideals of S inverse A and the primary ideals of A which do not meet S. So let us consider two sets, T to be the set of primary ideals of S inverse A and S to be the set of those primary ideals of A which do not meet S. Here S is multiplicatively closed subset of ring A. Now we need to define a function from T to S which is both 1, 1 and onto. So we consider a function from S to T by GQ is equal to S inverse Q. First of all, we will show that if Q belongs to S, then S inverse Q belongs to T. So that is, we need to show that if Q is primary ideal of A, which does not meet S, then S inverse Q is primary ideal of S inverse A. Now, in view of previous theorem, it is enough to prove that if Q does not meet S, then P also does not meet S, where P is radical of Q. So suppose if possible that S intersection P is non-empty. So take an element in the intersection, let that element be S. Then S will belong to S and Sn will belong to Q for some n greater than equal to 1. Again, by the same argument, we will get that Sn belongs to S intersection Q. Sn will belong to S because S is multiplicatively closed set. But we have assumed here that S does not meet Q. So therefore we get a contradiction. This means S intersection P is empty. Hence, by previous theorem, we get that S inverse Q is primary ideal of S inverse A. So that means G is well defined. Now we take a reverse map from T to S by HI is equal to IC, contraction of I, which is equal to F inverse I, where F is a natural homomorphism from A to S inverse A. Now, we know that contraction of primary ideal is primary. So, H will be well defined once we show that IC belongs to S. This set S, that is, IC does not meet S. That is, IC intersection S is empty. Suppose not. Suppose that this intersection is non-empty. So, take an element X in the intersection. So, we get that Fx will belong to I. But what is Fx? X by 1. And X is in S. So that means this is unit in I. So therefore I will be S inverse A, which is not possible because I is given to be primary ideal of S inverse A. So thus IC intersection S is empty. So this means for I in T, IC belongs to S. Now we consider G composition H of J. So this will be G JC. So this will be S inverse JC. Now remember, S inverse JC is nothing but JCE, which is equal to J. This is because we have proved that if J is ideal of S inverse A, then J is equal to JCE. Now let us take H composition G. So this will be H S inverse J. S inverse J is JE. So this will be JEC, which is equal to J by previous theorem. Remember, we have proved that if S intersection P is empty, then QEC is Q, where Q is primary ideal of A. So using this result, we get that H composed with G is identity, and we have proved that G composed with H is identity. So this means G is bisection. Thus we have obtained one-to-one correspondence between primary ideals of S inverse A and those primary ideals of A which do not meet S. Now, let I be a decomposable ideal with I is equal to intersection Qi as its minimal primary decomposition, and suppose radical of Qi be Pi. Suppose S is multiplicatively closed subset of ring A. And suppose Qi's are arranged so that S intersection Pi is empty for 1 less than equal to I less than equal to M, and S intersection Pi is not empty for the remaining ones. Then if these primary ideals which occur in the primary decomposition of I satisfies these two properties, then the primary decomposition of I gives primary decomposition of S inverse I and IEC. So this theorem says that S inverse I is just the intersection of M of these, and IEC is also intersection of M of these, and moreover these will be the minimal primary decompositions of S inverse I. Here it should be S inverse QI. S inverse I is intersection I is equal to 1 to M S inverse QI. So let us prove it. Now I is equal to intersection I is equal to 1 to N QI. So applying S inverse both sides, we get that S inverse I is intersection S inverse QI. Now breaking this intersection into two parts, first take the intersection of M of these and then take the intersection of remaining ones. Now since for these I's Pi intersection S is non-empty, so S inverse QI will be S inverse A. So we are just left with this S inverse I is equal to intersection S inverse QI, I going from 1 to M. Now again IEC will be intersection QIEC, I going from 1 to N. Again breaking this intersection into two parts, and since for these QI S intersection Pi is non-empty, so this will be just the whole ring. So we are left only with this, and this for these I's QIEC will be QI. So IEC will be intersection I is equal to 1 to M QI. Since this is a minimal primary decomposition of I, so this will also be minimal primary decomposition of IEC. Now let us define a new notion, isolated set. Suppose I is any decomposable ideal, that is, we can write I as intersection of primary ideals. So this means we can talk of Si, the set of associated prime ideals with respect to ideal I. Take a subset sigma of Si. This set sigma is called isolated if it satisfies this condition. What is this condition? Suppose P dash is any associated prime ideal with respect to ideal I is such that P dash is contained in P for some P in sigma, then P dash will belong to sigma. This means that no element of sigma will contain any element outside from this set. Or we can say that P dash does not belong to sigma will imply that P dash is not contained in P for all P in sigma. Now, with the help of this definition, I am able to prove this result. So let sigma be isolated set for decomposable ideal I. So we take S to be A minus union of all prime ideals in this sigma. So it is easy to see that S is multiplicatively closed subset of ring A. Now, suppose S is defined like this, then we can say this. For P in Si, P belongs to sigma if and only if P intersection S is empty. Here S is A minus union P in sigma. So let us prove this. Suppose P belongs to sigma, and suppose this intersection is non-empty. So take an element X in the intersection. So since X is in P, so this means X will belong to union P in sigma, but S is complement of union of P in sigma in A. So therefore X does not belong to S. But here we are saying that X belongs to S. So we get a contradiction. This means P intersection S is empty. Now let us prove the converse part. Suppose P intersection S is empty. Now we want to prove that P belongs to sigma, where S is union P in sigma complement in A. So let P intersection S is empty, and suppose P does not belong to sigma. This means P is not contained in P dash for all P dash in sigma. Now, by prime avoidance lemma, this means P is not contained in union P dash in sigma. This means P is contained in a complement of this, which is S. This means P intersection S is not empty, but we are assuming that P intersection S is empty set. So we get a contradiction because we have assumed that P does not belong to sigma. So therefore P belongs to sigma. So we will be using this theorem again and again. Now we are ready to define second uniqueness theorem. Second uniqueness theorem tells us about uniqueness of isolated primary components of a decomposable ideal. Suppose I is a decomposable ideal, and suppose it is decomposed like Q1 intersection Q2 intersection Qn. Suppose Q1 is a primary ideal whose radical is P1 and P1 is isolated prime ideal. Recall that isolated prime ideal is minimal element of set as I. Suppose Q1 is a primary ideal whose radical is isolated prime ideal. Then Q1 is unique. That is, if I take two primary decompositions of I, then Q1 will occur in both of that. So this uniqueness theorem tells us about uniqueness of isolated primary components. Recall that first uniqueness theorem does not tell anything about the uniqueness of primary components occurring in the decomposition. It just tells us about the number of uniqueness of associated prime ideals and the number of components in any two minimal primary decomposition. So let us see the statement of second uniqueness theorem. Suppose I is a decomposable ideal with I is equal to intersection Qi as its minimal primary decomposition. Suppose radical of Qi is Pi. Suppose Pi1, Pi2, Pim be an isolated set of prime ideals associated with set I. Then Qi1, primary ideal whose radical is Pi1, intersection Qit, intersection Qim is independent of the decomposition of I. That is, if I is equal to intersection Qi dash is any other minimal primary decomposition of I with radical of Q1 dash is equal to radical of Q1 and so on, then Qi1 intersection Qi2 intersection Qim will be same as Qi1 dash intersection Qi2 dash intersection Qim dash. This intersection is independent of any minimal primary decomposition. That is, this intersection will appear in any minimal primary decomposition of I. So let us try to prove it. So we take sigma to be this set. Now, and S to be A minus union P in this sigma. So it will be intersection A minus Pij, j going from 1 to m. As before, S will be multiplicatively closed subset of A and Pij will belong to sigma if and only if Pij intersection S is empty. Now, we take E and C to be extension and contraction with respect to homomorphism F from A to S inverse A. So IEC will be just intersection Qij, j going from 1 to m by the theorem we have done. And this will be same as intersection Qij dash j going from 1 to m. So this intersection is independent of any decomposition. But we have something more to say. Suppose I is a decomposable ideal with I equal to intersection Qi as its minimal primary decomposition. Then a primary component Qj is called isolated primary ideal if radical of Qi is isolated prime ideal. So the isolated primary components corresponding to decomposable ideal I are uniquely determined. This result will follow as corollary to this second uniqueness theorem. So for this, we will see first this example. Suppose A is kxy, I be the ideal generated by x square xy, P1 be ideal generated by x, P2 be ideal generated by xy, P3 be ideal generated by x square y. So in the previous lecture, we have seen that I has two minimal primary decompositions, namely P1 intersection P3 and P1 intersection P2 square. Now, in this case, Si is nothing but P1, P2. We can easily see that P1 is minimal element of Si. So therefore, P1 will appear. P1 is appearing in both the primary decompositions. So this is what the use of second uniqueness theorem. So let us try to prove it. Prove what? That isolated primary components corresponding to decomposable ideal I are uniquely determined. That is, if we have two minimal primary decompositions, suppose intersection Qi, intersection Qi dash, with radical of Qi equal to radical of Qi dash equal to Pi. Recall, we can write this because of first uniqueness theorem. This n is same as this n, and these two are equal. So suppose Pi1, Pi2, Pim be isolated prime ideals. That is, these are minimal elements of Si. So we first take sigma 1 to be Pi1. Sigma 1 is isolated set. So we take S1 to be A minus Pi1. So S1 will be multiplicatively closed subset of A. So if I take E1 and C1 to be extension and contraction with respect to homomorphism F1 from A to S1 inverse A, then I E1 C1 will be nothing but just Qi1 and same as Qi1 dash. So these two will be equal. Similarly, if I take sigma 2 to be Pi2 and take S2 to be A minus Pi2, again E2 C2 to be extension and contraction with respect to F2, which map from A to S2 inverse A, then I E2 C2 will be Qi2 is equal to Qi2 dash. So continuing like this, we will get that the primary ideals Qi1, Qi2, Qim will come in both the minimal primary decompositions of I. So thus, uniqueness theorems tell us about the uniqueness of isolated primary components. Like this. Thank you.